I want to talk about steels today because we're going to celebrate steels as far as the Taylor Lecture. I go back a little ways with the Taylor Lecture. The first one I attended was given by Professor Tom Eager from MIT, who passed away a couple years ago. Let's just say Tom was not one to go with the party line. He came and gave a talk to a bunch of structural ceramists and told them why basically ceramics suck. So he did not have a lot of favorable people. We'll say Professor Rustum Roy was in the room. He was not happy. I might do the same today, so I'm going to say some things some might not like. Well, that's too bad because you invited me to come and talk. So what I'm going to talk about, though, is I want to tee it up for Harry, because I do want to say a little bit about how Harry's affected me and affected a lot of us within the welding metallurgy and the sort of the metallurgy community, especially for sort of my age group. I'm not quite in Harry's generation, but I am damn close to it. So Suresh Babu is here from University of Maryland. He was your first Indian graduate student at Cambridge. And Suresh has connections here at Penn State. Professor Voigt is here. He has connections to Harry as well, as having taken his sabbatical rather than at the Pentagon in Cambridge. We'll see how mine works out. I think Bob's probably worked out really well for him. But we're going to talk about stainless steel. So I want to tee it up for a little bit of how important Harry really is when it comes to steel and what we've done. And I want to talk about stainless steels because they really get the short shrift when it comes to steels. Most of the time when we teach steels, we really limit ourselves to talking about carbon manganese steels, and people tend to imagine that they are old. They are. But steels are just fascinating, and basing on the iron system, the iron carbon system, the iron chrome system, the iron chrome nickel system, things get real complex really quickly. And there's just a myriad of things that we can do with stainless steels. Now, a little bit about Harry. That is not a typo. That is a steel metallurgist that has 66,000 citations in August. It's probably up to about 67, 68 by now. Harry has been just incredibly prolific. The books he's written created a few controversies with the Bainite book, I'm sure, over the years. But he basically wrote an entire book on Bainite, really with honeycomb. And my sort of relationship with Harry began even as an undergraduate. So one of the professors here who taught phase transformations in physical metallurgy was Professor Paul Howell. And so he was postdoc in Harry's group at Cambridge with honeycomb, I believe, right? So they were there. If you haven't read this book, this is a terrific book on geometry of crystals. And then a couple of others that he's done. He is Sir Harry, so that was him receiving his knighthood from Queen Elizabeth. As you can tell, he's got several of these honors. But I do want to talk about it's rare when you really think about, he was knighted for developing a rail steel. It's basically, if you go into Europe and you ride the trains, you ride the rails in Europe, you're going to be riding on steels that really Harry developed and really came up with, is these types of bainitic steels. And I will tell you, I work a little bit with people in the aerospace gear business as well through the Gear Research Center here at Penn State. And this is like the Bible. It is right up there, and to throw a shout out to Suresh's current school in Maryland, is the equivalent of George Dieter's mechanical metallurgy book as far as the Bible. When you talk to gear steel people and bearing steel people, this review article is by far the one they go to all the time. So just to give you a little concept of what Harry has done in the steel business, but if you are really interested, I would say go onto YouTube. I wanted to play a little bit of this in his own words, but this is just a really great description of a lot of the things Harry has done. And I know people like to listen to podcasts, and if you get a chance on BBC Channel 4, The Life Scientific, this was a terrific description, and really give you an idea of how you can take and study and really become an expert in something. You know, we might consider steels to be mundane, but you really look at what steels have done, where they are, how complex they are, how much of our basic sort of foundational knowledge within material science and metallurgy goes back to steels. It's really fascinating, and I highly recommend that every student should really listen to this. It is definitely inspiring and maybe give you a little bit of a motivation to continue doing what you're doing and going from there. So if I'm embarrassing you, Harry, too bad. So, but the other one is, he is the Todd Palmer, and if you are not a cycling fan, shame on you. He is the Todd Palmer metallurgist when it comes down to it. You would rather have maybe some of the other British riders, but Palmer has won 4 Tour de France's since 2020. And so Harry is an avid cyclist. If you look here, that is a 63-kilometer ride that he just did. And so he is an avid cyclist, and always one that I always am fascinated by. Not something I like to do around here, because drivers in Britain actually respect cyclists, unlike here in the US. So let's go back to a brief history of steel. Now, Professor Morrow said we're not going to look back. Well, you invited me. It's your problem. We're going to look back a little bit. And what we're going to see here is what I wanted to talk about is sort of this foundational knowledge, and to tee it up for what Harry's really going to talk about. I was sort of talking with a well-known physician, an immunologist, for some other reasons. And she was telling me of how fascinated, how she really held a certain antibody in high regard because she started her PhD work on it. And I said, I feel the same way about iron and nitrogen. It was Professor DeBroy, when I came into his group, he said, you're going to study nitrogen absorption in steel welds. I said, what? So all these years later, still the same. And so I still high regard. So I'm really looking forward to what Harry's going to talk about in a little while. But the early origins of steel, you know, we go back to 3000 BC, and we saw a nice one from Professor Bezak. But a bloomery furnace really started out. This is an early blast furnace. And we hear a lot of bad things talked about blast furnaces. We're trying to get rid of them. They are bad for the environment. There are a lot of these things. You know what one thing they're good at? Is making iron. They're really good at it. And why we can't displace them? Because you can't find anything better than a blast furnace. And it goes back to some of these early discoveries. Did they know what they found? No. There's a little serendipity involved. There's a lot of other things involved in these types of discoveries, but it was there. So we go to Wootz and Damascus steel. These are basically swords, so you can imagine. Today we spend a lot of money on defense in the US. Why did they develop these iron and steel alloys? Basically to make swords and weapons. So the defense industrial complex goes back a little longer than we might think. Early mass production, and then into what we can look at is like blister steel, where basically we were taking wrought iron and layering it with charcoal. Now, if you've been paying attention in the news a little bit, back in August there was an explosion at a coke facility in Clairton. And so a couple of the workers were killed in that explosion. Coke is what came after charcoal. So they started with trees. They figured out the energy density and the carbon content was high enough, so they went to metallurgical coal. And so I saw an article yesterday bringing up the idea of metallurgical coal as well. So back in the 1600s, 1700s, we start seeing these different things. Now what these are not really steels. What they are really high carbon iron alloys. So they're far beyond what we typically look at as steels. And even in Pennsylvania. So I'm sure that there's going to be a whole lot of people in town for some reason tomorrow. And a lot of them are going to drive past this. Anybody know where that is? Yeah, it's right at Porter Road. You've probably driven past it, never given it a second thought. It's the center furnace, so there's a mansion there. But this is basically why Penn State is here. As you can imagine, it's Pennsylvania politics. So there was a little bit of something given under the table to get Penn State here. He's the one behind it, of what it is. And so you start looking around, a lot of these in this old iron, and really what they made was a form of pig iron, and they converted that in. Now, there wasn't too much you could do with pig iron. It had all that carbon in it. What did that do? Made it brittle, made it not really easy to work with. Very simple shapes, very ugly kind of things. Now, it comes down to the modern origin, and we can look at Henry Bessemer. Found a nice picture of him. I mean, how can you not have a picture with sideburns like that on there? He figured out that if I blow enough air through there, he basically figured out how you make carbon dioxide. So he took oxygen or air, blew it through, was able to peel off all that carbon in there. Came in there, so some of the early Bessemer processes, we know how it got to the US. Andrew Carnegie, for lack of a better word, went and took it. You know, some people would say he stole it, which is probably a little closer to accurate. If you haven't read the Andrew Carnegie biographies, I highly recommend them. It'll give you a little different perspective on him. Brought us into open hearth processes. This is actually fairly modern pictures of it. There's still open hearth process mills in the former Soviet Union or in Russia and in Ukraine. But basic oxygen steelmaking by the 1950s really took things, turned things around, really brought it into what we can see as the modern steel industry today. Whether we can talk about some of the environmental issues of that, but that's not really what we're here. But being able to mass produce steel really brought us into sort of this modern era where we go past construction into a lot of the other items that we have and we really take advantage of, we really take for granted. Electric arc furnace. We're hearing a lot about, hey, we're going to take mini mills and we're going to make electric arc furnaces. Anybody been to Pittsburgh? The first electric arc furnace dates back to about 1907. The technology is not new. And so as we talk about maybe not wanting to look back but looking forward, what we're going to find here, and you can tell from all my gray hair, I'm getting old, and so I am taking on some of the ways of a curmudgeon. You know, a lot of these things were done 20, 30, 40 years ago. We are just now, and where you are is you're a little bit of a golden age because a lot of the tools that we have are so much better. If you look at the tools that Sir Harry and Professor DeBroy used, I remember an IBM workstation that was used in Professor DeBroy's lab that basically was a core, not even a fraction of the power of your iPhone or your cell phone, calculating weld pool dimensions. And Sir Harry, the TEMs you used back in Cambridge, in the early TEMs, and what you're able to do with them, even Lucille in the audience here, one of Professor Howell's students, really working on that. But this is actually in Station Square. This was one of the first electric arc furnaces. So we have an alumnus here who was a CEO of Crucible Steel. He lives in town. He comes around every once in a while, Jim Beckman. So he would know that because that was one of Crucible's original arc furnaces in Syracuse. So this stuff goes around, and a lot of it has been there. And so to understand the steel industry and understand a lot of when people are talking about green steels and what some of the issues are, is a couple of things you need to understand. There's basically two routes that the modern steel industry looks at. One is what they call an integrated route, and that's what involves a blast furnace. That's where you start from ore, you work your way, you make pig iron, you convert it into steel. Or electric arc furnace steelmaking, where your input can be what they consider direct reduced iron or scrap. Where does scrap come from? Scrap basically comes from automobiles. So when you see car shredders, when you see people bringing things in, your old washer, your old dryer, that's the scrap, and that's the feedstock that's used into that. So a lot of taking away a lot of this energy, people will tell you that, oh, well, I have electric arc furnace steelmaking, it can easily get me there. To a point. One of the things that I'm going to talk about, and I'm going to let Professor DeBroy talk about this a little more as we key up for what Sir Harry's going to really talk about, is what goes into scrap. What's in the scrap material? You don't know. And so you start getting contaminants, you start getting other things in the scrap material. These are going to lead to issues in the steel that are going to be a lot of what I'm going to talk about here later, is how complex they are. Now, there's some emerging green technologies. We see the electric arc furnace keeps coming back there, and I keep hearing this talk about this, but I keep not hearing a lot of people really talking about what other problems arise from this. What other things are process engineers, what other things are you as students going to be expected to be able to deal with? and what skill sets you're going to need to be able to do that. Green hydrogen, basic direct reduction. Once again, I will slip into my curmudgeon. If you would read Turk Dogan's old papers from the early 70s, you will see that they were talking about this in steelmaking literature at the old Bethlehem. I think somebody mentioned Bethlehem Steel, the Steel Research Center. They were talking about this kind of thing years and years ago. Same with molten oxide electrolysis. Professor DeBroy's first graduate student is Uday Paul. He was at MIT and at Boston University. He'd been talking about the use of molten oxide electrolysis for what, Professor DeBroy, probably for 35, 40 years now. So that's a little bit on there, but let's think about what makes stainless steels unique. Hopefully these look familiar. If not, I have to have a little discussion with some of your other professors here. So there are some common tools here. Now, what I'm going to tell you is these tools look simple. Why do they look simple? Because a lot of people put a lot of work into developing the experiments to come up with really elegant engineering tools. If you go back, the namesake of Bainite, Edgar Bain, at the U.S. Steel Research Center, they did just groundbreaking work coming up with time temperature transformation and continuous cooling transformations. It is amazing the amount of data they were able to extract from a series of S-curves and a number of experiments done on Jominy and quench tests. So if I'm speaking, you don't understand these words, you're going to have to look them up. But I would be happy to talk to you about them. But there were just common tools. The iron-carbon phase diagram. These types of tools are there. It led us into really sort of the fascination that there is with steel. And if I do sound a little excited about this, it's because it is sort of really exciting from an intellectual standpoint. You think of something as simple as an iron-carbon system. I can change a small amount of carbon between 0 and 1 weight percent, and I can absolutely change every property of that steel. I can take a 1045 steel, which is this one, and so the dark areas are perlite. That's pro-eutectoid ferrite that forms on prior austenite grain boundaries. Just think of all that jargon I just threw out there. Describes something that's so simple. It's an iron-carbon system. Has a little bit of manganese in it. It's not considered new. It's not considered anything else. It gets its own classifications as we go from a 1005 to a 1045 to a 1080 steel, work our way up. If I want to heat treat these differently, I can get all kinds of different properties just out of this one steel alone. I can tailor that microstructure. So when people talk about process structure property relationships, it really starts here with steels. And this is where a lot of our understanding went. Now, sort of going here is on the end here. I'm not going to talk about tool steels or some of the other high alloy steels, but stainless steels, how important can they be? A little bit stuck here off to the side. Well, if they make a DeLorean out of it, well, I mean, how much more can it be important than that? I'm not going to put the other stainless steel vehicle because this is a much more attractive looking vehicle than that is. It's amazing. I watched one of those. Anybody ever watch one of those motorcycle building shows? I watched one there, and Jesse James was on there. He's going to make a bike out of stainless steel. And anybody know who this is? This guy builds bikes. Apparently doesn't know anything about stainless steel because he sat there and he kept trying to quench an austenitic stainless steel. And he thought he was going to make it stronger. Could not understand why it never went stronger. I was like, idiot. But, you know, you've been to the Gateway Arch, welded stainless steel structure. Chrysler Building, same thing. In Europe and in Sweden, this is actually a duplex stainless steel bridge. And it sort of starts out with what makes a stainless steel. Usually it is we take iron and chromium between about 11 and 30%. So what's the first thing we do as metallurgists? Hey, let's get an iron-chromium phase diagram and say that's going to describe stainless steels. Looks a lot different than an iron-carbon phase diagram, doesn't it? So not even really close in how they go about it. Now, you start getting some interesting features here, and this was one I grabbed this off the internet, off the Google machine. And if we look at stainless steels, there's actually different classifications that we can look at. And basically, because as I usually tell, so I teach the introductory materials class to the mechanical and industrial engineers. So I've taught that for years, not teaching it this semester, obviously. But when you look at materials people, especially metallurgists, are just Captain Obvious from that corny commercial that was out there. If it's in the title, it's there for a reason. Like ferritic stainless steels. What phase do you think they are? They're ferrite. You go to austenitic stainless steels. They're austenite. So it's the BCC, FCC. So everything's like right in the titles. Duplex, a combination of the two. Martensitic. Where did these come from? From just the iron chromium phase diagram. Iron chromium phase diagram is pretty simple. There's not really a whole lot to it. It's got a couple interesting little features to it. But you can see as I are changing that, I can make magnetic steels. I can make non-magnetic steels. I can start getting into all kinds of things. Now, my wife likes stainless steel appliances, and that was a requirement when we got married. There was none of this others. Everything had to be stainless steel. I was like, fine. Until I looked at the price tag, and I said, well, I better get to work. But so we tend to see ferritic stainless steels, and we see them in all kinds of things. We see them in appliances, architectural elements, exhaust systems, and automotives. The number of vehicles we build in the US, you start thinking of ferritic stainless steel and it goes into the exhaust system. Pretty fascinating. Austenitic grades, that school in Columbus has made a career out of looking at weldability of austenitic stainless steels. How many careers do you think, Suresh? I think probably like 10. Probably at least. They have spent their whole careers talking about weldability and cracking susceptibility of austenitic stainless steels. Now, martensitic grades are what I'm going to talk a little more about. These are really fascinating ones that just get largely ignored. Every razor blade you have, every scalpel, you go into surgery, there are martensitic grade stainless steels there. Cutlery, surgical instruments, bearings. You fly on a rotorcraft, you fly on anything that Pratt & Whitney or GE makes. There's a martensitic stainless steel stuck somewhere in there. So these are all important, but when we're looking at these, they're made from more traditional routes. And basically what made the materials industry and what made the steel industry so good is they got very good at making very common shapes that could be widely used. And so a lot of my background is in welding and joining. And if you want to build something, you need to weld it. So most materials companies started out basically their wrought processing. This is where you start getting into basically continuous casting, how I'm annealing it, heating it up, rolling it into shapes. So I can make wire, I can make plate, I can make all kinds of different types of extrusions, coils, which are just basically thin sheet, bar product or long product, all across the state of Pennsylvania, whether you're going to Carpenter, whether you're going to ATI, whether you're going to whatever US Steel is now, whatever they're called. These different companies make all of these. And stainless was always a route for them to go to what they called a higher end market. They're more complex, and we're going to see the complexity of stainless steels here soon. Now, part of this is as we start getting into some of these advanced manufacturing areas, what we're going to start doing is working with different product forms. So we're going to get away from some of these different shapes, and we're going to get into powders. You want to talk about making something complex even more complex? Take a powder and weld it with a laser and really look at the physics involved in what you're doing. Most sane people would have told you, like, that is crazy to go do that. You have taken everything bad about what we've done and everything beautiful about the microstructures and the process structure property relationships that we've designed all these alloys for, and you're going to make it into a powder and melt it with a laser. Just pure insanity of what we're going about. Now, even in the additive space, this is my little it's not new either. Don't let anybody tell you that this is new. Actually, a Pennsylvania company came up with it in 1925. Looks like a WAM-based process to me, but Westinghouse, the old Westinghouse labs. You drive down the parkway in Pittsburgh, you will see these. You will see what's left of the old Westinghouse Tech Center. It's pretty sad when you go past it. It looks like apocalypse there, but they came up with the idea of making decorative things. Looks like a WAM-based process. By the 70s, we had seen the development of some of these powder bed fusion, even into the 90s. Now, this is where I sort of was introduced to it, really sort of in the second generation. of it, where the national lab started developing lens and directed light fabrication. There's actually a company up until about 2005 that was making titanium forgings. They went out of business. So you can imagine why things sort of went to where they were. Now, what really drove a lot of this, it's a little bit of a misdirection from steel, but just for a lot of the students to understand, why do technologies get displaced? You have to do something better than what's already being done. Why haven't we displaced blast furnaces? Because they're too good at what they do. Now, in the additive space, there took some enabling technologies to get it to where it is today. Basically, the introduction of fiber lasers was the big one. That was the one. A reliable laser that didn't use helium as a shielding gas. Motion control and robotics, and then computational power. We hear about that constantly today. What we're going to really realize here, I think, soon with computational power is all those other things that we need, like power generation, water, copper lines, transmission lines, all of that are going to be a big part of that because you need to power the brains behind it. Now, the AM processes, we're not going to go too much into this, but powder bed fusion, directed energy, everybody hears about this. I always like to concentrate on the powder side of it and the materials side of it, and more so of how complex it is. You start looking at what we're doing. We talk all the time as material scientists and as metallurgists of process, structure, property, performance relationships. We have a tetragon. It used to just be, when I was a student, it was process, structure, properties. But we had to get the third dimension in there and make a tetragon. So we came up with some idea of performance to add to it. But you start with what is in the powder. How the powder feedstocks behave is one, because this is a simulation from Livermore. It's a little dated at this point, but completely unrealistic in how powders actually pack. Completely. It's just like, it's a fantasy of how powders pack. Melt pool dynamics with what Professor DeBroy has done over the years, the defects we have. But post-processing is always there for us. And you start thinking about the complexity of these alloy systems and what we're going to run into. You've got ones, and one that I'm big on is variations in alloy compositions. We're going to see how much they actually vary, especially in stainless steels. And an ode to Sir Harry here is role of interstitial alloying elements in powders. So in AM, as we start talking about additive manufacturing, we start talking about advanced manufacturing, we start going to powders, they start picking up oxygen. What is oxygen going to do? What is the extra nitrogen that's picked up in the powders going to do? For that matter, what is boron going to do? I'll tell you, I've looked at it, stainless steels, and as we start looking at the scrap stream getting contaminated, it's going to have boron. It's going to have a lot of these other things, copper into it. And the other one is sort of like developing material property data sets. This is sort of the one that comes down to it. Now, we spend a lot of time in sort of the AI, the ML field, talking about really trying to understand processing. What do people actually use, or what do our end users, what do our designers, what do our manufacturing engineers, what do our really mechanical engineers need? They need material property data sets that are accurate and reliable and have small levels of scatter. That's what MMPDS is, the metallic material property data sets. So I'm probably speaking Greek to most of you with that, but MMPDS will be a critical part of your life right up there with ASTM. And so these are a couple things to really focus on. Now, how complex are they? So I don't know if anybody's working in high entropy alloys, but I will tell you, if you're working in steels, don't let them pick on you. High entropy alloys are simple. There's 5 components to them. They don't do too much. Now let's think about what goes on in a stainless steel. All right? So an austenitic grade alone, I got 1, 2, 3, 4, 5, 6, 7, 8, 9. They don't measure nitrogen, oxygen, or boron, but they're important. So I got like 13 components. So 5 versus 13. Where's the complexity? Complexity is here in a simple 316L stainless steel. Because a lot of things can go wrong, especially when you start processing it with additive processes. You talk about 17.4. I've got 8 heats of this material sitting in my lab. It heat treats 8 different ways. We can't figure it out. Duplex grades. I see one of my former students, Andy, here. He spent a lot of time talking about these. Duplex steels are fascinating, the ones that we don't use here. Now, how did we get around this as metallurgists before this? Is we simplified things. And we came up with different plots. So this is a feature that I took out of a WRC, it's a Welding Research Council 1992 diagram looking at modes of solidification for stainless steels. If you go to that school in Columbus, this ought to be in like the motto for the school. This is what they've really focused their work on in their welding engineering programs. So you see ferrite numbers, you see austenite, austenite, ferrite, ferrite, austenite, ferrite. You've got these changes in solidification modes. And so they took complex compositions and they came up with equivalents. So they came up with simple numbers. So when you really come down to it, what we're trying to do is make everything look like a binary phase diagram. We're trying to put everything in 2 dimensions. Because we all think in 2 dimensions, because we've been taught forever that we take a sample, we prep it, we look at one slice of it in 2 dimensions, and that describes everything about it. Is that true? No, not at all. And so the other one is where computational thermodynamics. So that iron-carbon phase diagram that looks so simple, so if we look, these are for 316L stainless steel, and what the difference here is a slight difference in the amount of nitrogen. And what we start seeing is sigma phase is not something you want. If you're going to have corrosion problems in an austenitic or duplex stainless steel, sigma phase is going to be somewhere to it. And it just shows you how complex, even at small amounts, these different secondary phases can play a role in leading to defects, leading to failures, and it's always the failures you don't expect. It's always those catastrophic failures that occur, especially in things like fatigue. That's why, as most academics, we test everything in static tensile loading, because it's something we can sort of predict. Now, these are violin plots, and this just gives a little bit of an idea of how complex 316L is. So what I had a student do is go into the literature and grab every composition that people did report. So what people report in compositions is a problem, because not everybody reports everything. And said, let's plot them on this and figure out what we have. So the red lines are what the ASTM standards for the alloy are. As I said, as you can tell, is the number of components we're talking about here and the complex interactions between all of these just make this, 316L, you could spend your whole career talking about this one alloy. There's 150 commercial stainless steel alloys out there to really think about. So in this one, these give you variations in composition. I'll tell you, if you vary between 0.5 and 1.5 manganese in an austenitic stainless steel, you get 2 completely different alloys. They won't even behave. Their behavior will not even be close to similar. We've had issues with a nickel-based alloy 625, where we saw a 25% difference in yield strength because of a slight change in the iron content. So these, even within these allowable ranges, there's issues. The other issue is apparently a good number of people in the literature don't understand what a 316L standard is, because they've reported 316Ls with chromium levels outside of the allowable ranges. So is it really that or not? Now, these other role of minor alloying elements, how do they impact it? So I'm going to jump to a 17.4 as a precipitation hardened stainless steel. You'd say, what's that? This is used constantly. About every turbo machinery component you can think of has 17.4 somewhere in it. And so it needs to be, basically the precipitation hardening means it needs to be heat treated. And so we do a couple different heat treats to it, but once again, this was the same type of idea, is how much do things vary? And we started looking at this. So what we saw were these huge variations in different heats of material. Now, I've had reviewers come to me, it's like, what's heat-to-heat variability? And I would say, basically, shame on the journal editors for having these people review articles. Because heat-to-heat variability is going to be something that, even if you're in a different field, not in a metallurgy field, that you're going to have to worry about. Because what it is the scatter and the data that we have, and how different materials can vary. But you start looking at the heat-to-heat variability in even these, and this is just in powders. This is just a small subset. They can vary significantly. What I want to tell you is that is the differences in the mechanical properties out of them. And that's just ones we grabbed out of the literature. And these are additively manufactured, powder bed fusion, pretty standard alloy. So I don't know as a designer how you're supposed to be able to do that. Now what we did find was that when you heat treat these, it's supposed to be peak aging at a low temperature and overage after that. We actually found that a whole portion of these actually got harder as the higher temperatures we aged them at. And so some differences there, but I do want to talk about something else. So we have this issue with heat treating. I want to talk about oxide inclusions a little bit. And I know Andy's happy about this because there's a lot of his work from his PhD work with me, is when you have a wrought material, they're easily able to control the oxygen contents in them. So if I take something and I roll it and I go through all of this really just love and care that I put into that steel in order to get it into this type of microstructure, I'm going to have a low amount of oxygen. I'm going to make it fairly difficult to form oxide. So I'm not going to have a whole lot of oxides. I'll see some oxides here or there, but not a whole lot. Now, when I take it into powder and I add a little bit I increase the oxygen content just a little bit from 0.04 to 0.02. I mean, really, what's 1/100th of a weight percent among friends? It's not very much, right? Unless it's a gas. What I start seeing is this spinel phase, which is a chromium manganese oxide, actually starts to form in the liquid, which means, can I heat treat my way out of this? No, it's there forever. So until you do something else. Chemical engineers have a little statement that they make. Dilution is the solution. And so what that means is, how do I get rid of it? I add more iron to it. So I need to dilute it and make that amount smaller. We do that with copper all the time in steels. In order to get the copper levels down in the scrap stream, you just add more iron, you add direct reduced iron. But what you start to see here is you can start forming a lot of oxides, and they appear in the powders, and even so people say, oh, it's just on the outside of the powder. Nope. This is a cross-section of a single powder particle. It shows up in there too. And when we started really looking at it, it actually shows up as amorphous because of the rapid cooling rates of the powders as we produce them. And they will develop as you start increasing the heat treatment of it. So if you start hot isostatically pressing it, you start doing all these things. You start running into an evolution of this inclusion, and sooner or later it will show up all over the place as you start looking at your additively manufactured component. The issue becomes, and there's some thought there, is, hey, there are oxide inclusions, there's oxide dispersion strengthening, right? When we start looking at really in static mechanical, that's fine until we do things at low temperatures. Red is bad. So a wrought material is usually about 100 so joules of a negative 45 degrees C impact energy, Sharpie impact test. We were breaking them at like 8, 20. So the oil and gas industry says no way to using these because of that. Now, why is that? So a lot of it has to do with the size and shape of the ferrite and austenite phases, but a lot of it has to do with all of these inclusions sitting all over the place, going back to the role of interstitial gases in there. And so even in austenitic stainless steels, you say, well, it's a problem in duplex stainless steels. Well, they show up in austenitic stainless steels too, whether I have a certain amount of nitrogen, low level, high level of nitrogen or not. Show up in basically 17-4s. They're there as well. And what you notice here is sort of like different names here. All the oxides are different. And so the complexity of these starts to go. Now, if you're a fatigue person, that's never something you want to see. That's what we'll call a tire track. So that is an oxide inclusion that actually on a fatigue surface like basically left little indents as it worked its way up. So we've got a lot of complexity in these alloys. And that's mostly what I wanted to sort of get across to you today, was that Stainless steels are complex, and Harry's going to talk a lot more about the basic science behind nitrogen and oxygen in these. And as we start seeing the differences in the compositions that are there, that they're going to have impacts on what happens. Now, I wanted to sort of hit on this a little bit. So I had one other student. He's also at NIST and probably sitting pretty close to where Andy sits down in a materials measurement laboratory at NIST in Gaithersburg. He has a National Research Council postdoc fellowship. So if you haven't looked into those as a postdoctoral opportunity, I highly recommend those as well. Those are very good opportunities and very prestigious. So sort of comes down to, as material scientists and as metallurgists, our goal is really to take what we do in processing, develop properties that designers can actually use. So we're critical in any of the design aspects that come along. Now, when we start thinking about how do we ensure safe structures, material properties are a pretty important part of that. They're critical to it. And most designers are only going to take data that they want or that they can use that they have confidence in. Now, how do you develop confidence? You basically show that there's a limited amount of scatter. So there's a requirement of statistics. So I've been recommending to most of my students that, especially as a metallurgist, because we're metallurgists mostly because we don't like math that much. And so what you should do is start befriending a statistician, because that's really where the big data and the data analysis is really what's coming out. Because up till now, really, as metallurgists, a lot of what we've done has been a data sparse environment. We get 1 or 2 experiments, they're expensive to run, we take that data, we run with it. Now there's more needs to start looking, especially as we look at some of these data sciences, AI, ML, whatever we want to call it. They're requiring these large data sets. And so we don't have the money to produce the testing of that. So one of the things would be to really think about, how do we produce the data to support this? Because the models are only good as the data that goes into them. I'm apparently a little bit of a Luddite when it comes to this, but garbage in, garbage out still matters. And so you can fool LLM models. You can corrupt the data sets. You can get them to tell you just about anything if they don't have good data going into it. So where can we get some of that data? The literature is rife with data, if you really look at it and you go back and really start searching for it. And so I had a student, like I said, down at NIST. He did this just looking at 316L stainless steels. And so I wanted to throw this here. So Wrought conditions. So we look at, usually in the AM field, people will tell you it's like we're lacking data. We're lacking well-pedigreed data that we have. And what we're going to see is most scientists and academics have done a really poor job of reporting the data that they've produced. And so there hasn't been a data dictionary, there hasn't been a common methodology to report the metadata that goes along with just a fatigue test. There are cases in the literature where we've looked where people haven't reported an R value for their fatigue testing. And if you do fatigue testing and somebody doesn't report an R value, it is completely worthless. And I know you're laughing, but we've seen this. It's amazing that this stuff got published, and sometimes even in reputable journals. But we look at the amount of data here versus what the Wrought conditions are. It's not so much that we don't have a lot of data points, it's that they're scattered all over the place. There's no trend line to them. And so what we can do is start thinking about taking that data and being able to operate with it a little bit. So there's a lot of data out there on the AM side. A lot of it is difficult to use because it doesn't have a lot of the metadata that you need, but a lot of the metadata, sort of things like material properties, testing conditions, processing, things you've done to the material in order to get those parts, those data or those properties. One of the issues is there's no data dictionary. There's no set sort of definition that we have for everything that comes out and about. And without that set definitions, people can call it anything. And so you've got, and this is where a lot of the models tend to fall apart, is when they start looking in the papers that are out there trying to extract the metadata, there's not a common data dictionary for them to go to. And so one author may say one thing, another may say another, but it's actually the same thing. And so when we start talking about sort of the expertise that goes into it, that's sort of where it goes. Now, what I just wanted to sort of jump to here was sort of some of the work he did. You see a lot of data, but really of this idea of contributing and going into the data and being able to identify the role of defects versus microstructure, even in fatigue for 316L, and sort of bringing us to sort of where I want to end up today, and sort of hopefully teeing it up for Harry to really give you a good lecture on oxygen and nitrogen effects, and hopefully for Professor DeBroy to tell you about critical materials and scarcity. But AM materials, these are multi-component systems, and we can say about AM material systems in general, but stainless steels are compositionally complex alloys at the end of the day. And as we start looking at advanced manufacturing techniques, we're really subjecting them to conditions that we've never really expected them to. I used to joke with people as far as the Ti-6-4, especially when additives start to come out, is the designers of Ti-6-4 are rolling in their graves at what we're doing to the alloy and expecting it to perform in certain ways, because we've completely forgot about process structure property relationships with that. The other thing is these interstitial alloying elements are going to be critical. Our understanding of the role of oxygen and nitrogen in stainless steels is really going to be sort of the game changer that comes around, especially as we start talking about the scarcity of common elements like nickel, chromium, manganese. Anybody know what the critical materials list that the US government, USGS, produces every year? Take a look at that. About a third of it are critical elements to steels, stainless steels, nickel-based alloys, titanium alloys. It's not just about batteries and magnets. It's about every component of what we look at as our modern lifestyle. And so the last one is befriend a statistician. So that's what I have today. I'm sure I went over. I always do. But I'll be happy to take any questions.